getting most of your current. Maybe even an oval would be the most ideal shape. So I don't know if I've got a D battery handy. Does this take a... Well, I don't want to spoil the fun, but basically if I connect this to a battery, it would rotate. I just need current to run through this loop, and it would just keep rotating like that forever and ever and ever. So the commutator bit, is that not on this slide? Oh, okay. Well, I'll talk about it right here. So how a commutator works is in the Book's diagram, which is a little bit confusing. You've got this loop of wire, and on either side you've got a semicircle of metal with a little gap between this spot, and then a loop with current running through it and brushes. So the brushes make contact with the semicircle, and so when the red semicircle is in contact with this brush, it's going to drive current around the loop, what is that, clockwise. And then as soon as it flips and the blue becomes in contact with it, that's going to drive the current counterclockwise in the loop. So that's more of a fancy commutator. Our kludgy commutator isn't really a commutator. What our kludgy commutator does is, on one side, we sand off all of the coating on this magnetic wire so that it's in contact with our battery all of the time. On the other side, we shave off the coating on half of it. And so any time that the other side's covered in red, 180 degrees of its rotation, it's actually not completing the circuit. So this loop only gets current for half of its rotation. And the only thing that makes it go all the way around is momentum. So you have to give it a kick to start. But once it has momentum, it will keep rotating because it's getting current half of the time that it's rotating. So it's basically current, none, current, none, current, none. So it works. Okay, so we had a problem 2746. Yeah. Oh, go for it. Please ask questions.
Used to change rotation with them.
It just causes the current to switch directions every time.
That's what they do in electric motors, right? When they have commutators in them?
Yes, yeah. So it's the same thing in an electric motor. I'm not sure if, it's been a long time since I took my electric motors class, but is the electric motor in your car driven by direct current or alternating current?
Alternating.
Is it alternating?
Yeah, that was direct.
I'm not, I'm not the person to ask. There's a lot smarter people on this campus who build motors, but if you have alternating current, that's basically taking care of flipping the current direction for you, and so that's really helpful if you've got electric motors to put in alternating current. With direct current plus a commutator, then you've got constant current and then it switches direction. And so you get this square wave if you were to measure it on a signal generator. So if you're at your house and you could plug it into a wall, anything coming out of your wall is going to be AC. And then the car is going to have either a commutator or AC motor.
In the car one, I know that Tesla uses AC. They use AC. I have right here. I was looking. But no, it's more efficient with the power that you have instead of like a DC plus a commutator or whatever. I've never actually heard of that, but it's just more efficient with the current that you have, and so that's why I'm betting it's in any car, not just the
Also, I think the rare magnets are probably pretty expensive
yeah.
to source that material.
Oh yeah, they make electromagnets, which, right, cheaper, much cheaper. All right, so let's see what this problem was that I had relating to motors. Oh, these aren't really motor problems, are they? They're just, is this the same problem? Oh, the solution, I see. Okay. So 2746 is more like going back to the theory behind a rotating loop with current running through it in a magnetic field. So this is more of a physicsy problem than an engineering problem. So it gives you your dimensions. Going back to this equation, that would be your A and B dimensions. It gives you the current. It tells you that the loop starts out perpendicular to the B field. So that's flat on this page. The B field's going into the page. And it gives you the B field is 1.5 Tesla. So part A, there's no well, the angle would be 90 degrees because it's perpendicular for the net torque. Yeah, Chris?
So torque is force, correct?
It's not exactly a force, actually. It's units. The units of torque are newtons times meters.
So we couldn't use this torque formula. If we knew, for example, the electric field, the area of the coil, and our current going through it, we couldn't use that then in our sum of forces equation, knowing the mass of the coil, to figure out how fast it's going to accelerate. Acceleration's going to be.
You wouldn't use your torque answer, but you can use the force equations that we summarized on this page. So this page summarizes the forces on all sides of that loop. And in this problem, your angle, for part A anyway, your angle is 90 degrees and 90 degrees. So these would be, you could do your sum of forces.
For instantaneous acceleration, but it'd be tough to figure out, like, because as the angle is decreasing, so is that force then, right? Until it gets to zero and it's perfectly, you have to factor in momentum.
So actually the way to do it, and we didn't do this in 221 at all with rotating objects, is there's another relationship, and if you don't want to hear this, just tune out because it's not on the test. But torque also is equal to I alpha, so this is like mass times acceleration for F equals ma. This is the same thing, it's just it's like rotational force, and inertia is rotational mass, and then this is rotational acceleration. And so rotational acceleration we learned was omega times r squared. And is that right? I think so. And so your inertia is usually, it's some constant, I'll just say x times mr squared. And then alpha you can put in as omega r squared. And then if your torque equation was INBA, and if it was sine of 90, then this combination of things you could figure out, you could figure out your rotational, your angular velocity would be something. No, this was acceleration times r squared. Because that was the thing, is you could go from angular acceleration and get your radial acceleration. I think that's radial acceleration. Don't quote me on that. I actually used to teach that in this lecture, but it would just take like twice as long. So it's been a couple years. I'm a little rusty on whether this is the translation or tangential acceleration that would cause the loop to speed up, or whether this is radial acceleration that's just, if you had a constant velocity, that would be the acceleration pointing towards the center. I'm not remembering that. And I'm also guessing here. This is AR or AR squared, I'm not sure. I think it would have to be AR.
I'd like, if it's tangential acceleration, then it would be
oh no, this is A over R. A over R, yeah, unit-wise I was doing that. It would have to be meters per second over meters to get radians per or meters per second squared over meters. So that would get rid of one of these. Yeah, so that would be how you could get from the torque equation to an acceleration.
Got it.
Yeah.
Thank you.
Yeah, no, it's fine. Okay, so let me just verify for the force. Okay, so this is basically summarized on here. The sum of forces equals 0 because it acts, all the forces are equal and opposite. So for part A, the sum of forces is 0. And then B, then it says the coil is rotated through an angle about the axis shown. This is a little bit weird. So if you imagine this is your coil sitting on your paper, it's being rotated like this. So it shows that axis down the middle, so that's how they're rotating that coil. And it rotates it, rotated through an angle with the left side coming out of the plane and the right side going into the plane. Calculate the net force and torque that the magnetic field now exerts on the coil. They don't give us an angle. So we're just supposed to put it in terms of theta? 30 degrees. Oh, is that missing? Through an angle of, through A, okay, so right between that words A and angle, there's a missing 30 degrees. Through a 30-degree angle. Otherwise, this is an impossible problem. So the torque then is easy because you can just throw in the 30 degrees. We already have the net equation for torque. For the forces, it says the net force is still 0. All right, so I'm just going to, go ahead and say look at the solution because they've got a picture here that helps us visualize this. So the forces on these sides of the loop are easy to see. They're always, even as you rotate that loop, they're always going to be equal and opposite. But as you rotate this loop, these forces are like sort of off center. So it's a little bit hard to see. But if you look at their drawing where they do this side view, the forces may be off center, but they're still equal and opposite. So they're still going to sum to 0 just like in part A. So, so really, the main part of this problem is just solving the torque equation. That's the only one that's actually going to give you a different answer. So, any questions on this one? Problem 2746? Okay. Okay, so we talked about the commutator. There's a whole bunch about motors in your textbook that I'm not covering today. And example 2711, is this an actual motors problem? Okay, this one is. So why don't you guys try, oh, power. We didn't actually give you guys a power equation. Okay. So it's the power equations here, I'll just write them on the board, are not new for the DC motor. So when they ask you power stuff, it's the same power equations we've been using. Power equals current times voltage, or if you're talking about some resistor or resistance, then the power dissipated by the resistance would be, you could do I squared R, or you could do V squared over R. So that's necessary for part C. Oh, and then efficiency, we haven't covered that yet. Efficiency. They say P output over P input to calculate efficiency. Now I see why we're just reviewing this solution, because pretty much everything we haven't really gone through. So they give you the internal resistance, the voltage is 120 volt line, and then it's drawing 4 amps of current. So for part A, the EMF of the rotor is just they're using that EMF definition that we learned a while back. So if you're looking at that solution, VAB is equal to the EMF plus the internal, the current times the internal resistance. So VAB equals EMF plus I times R. And they rearranged that and solved for the EMF. So that's kind of a review problem. And then part B, they wanted you to solve for the power delivered to the motor. So that's using the I times V equation. And then the V in this case is that VAB, not the EMF. I'm not really sure why they even had us solve for the EMF, because we're not ever using that in any of the other calculations. So. C, they want to know the power dissipated by the internal resistance. So if you use I squared R, this R is the internal resistance. They gave the 2 amps. And then the mechanical output that is actually driven from the electric motor would be the power input you calculated in part B minus that power lost due to the internal resistance. And then they did P out over P in to calculate the efficiency, and this motor was 93% efficient. And then F, I don't know how we would solve this, so we'll just read it. What would happen if the machine being driven by the motor jams so that the rotor suddenly stops turning? It says, with the rotor stalled, the back EMF, which is proportional to rotor speed, goes to 0. So the current becomes I equals V over R, which is 60 amps. Then the power dissipated in the resistor would be 7,200 watts. That's a lot. So it says, if this massive overload doesn't blow a fuse or trip a circuit breaker, the coils will begin to melt. When the motor is turned on, there's a momentary surge of current until the motor picks up speed. This surge causes a greater than usual voltage drop in the power lines supplying the current. This is similar to the effect of your lights dimming when a big power hog gets turned on, like your dishwasher or something. Okay, it's kind of a, I don't know why I have that problem in here. All right, so that's it for motors. My battery's still going. Any questions? Any more questions about these motors? You're going to have fun building them. And building them is a whole lot more fun than me talking about them. So hopefully that'll be fun. So why don't we take a 5-minute break? And it's 1:30. Let's do the lab first, and then if we have time at the end, we can do this group activity. Sound good? Okay. Chris, can you turn off that camera for me?